Jai Hind to all of you. Today we are going to study addressing modes of 8086 microprocessor. This topic is covered under Unit 3 of Microprocessor subject, which is a core subject of Computer Science branch. So, we have already discussed what is a microprocessor. Previously, we have discussed 8085 and 8086 microprocessors are 8-bit and 16-bit microprocessors. So, 8086 is basically a 16-bit microprocessor, wherein we can say that its data bus is 16-bit and its address bus is 20-bit. Means 8086 can access a memory of up to 2 to the power 20, that is 1 megabyte of memory. From memory, it captures all the opcode and operand. So, the way in which microprocessor 8086 fetches or takes data from memory will constitute different type of addressing modes. So, we can say that addressing modes are basically used by a microprocessor to address data from memory. In 8086, the data bus is 20-bit, that is whole memory is of 1 megabyte. And we have divided this memory into segments. Each segment is of 64K and there are total from 1 to 16 segments. So, we can say that the overall 1 megabyte memory is divided into 2 to the power 4, that is 16 segments of 64K each. Out of these 64K, yani ki out of these 16 segments of 64K, only 4 segments are accessed at a time by a single program, which are called as code segment, data segment, stack segment and extra segment. So, the way in which a microprocessor fetches data from these segments will constitute addressing modes. And if we talk about memory, we can see that each segment is of 64K, that is its address bus is of 16 lines, whereas the overall address bus is of 20-bit. The 20-bit address bus will constitute the physical address of memory, whereas the 16-bit address will constitute effective address. So, the calculation to convert effective address to physical address is that we will shift this effective address by a bit to the left. That is, if we can say an example, let effective address is 2000 and the segment which it belongs is data segment with address 3000. So, the actual physical address will be 3000, which is left shift by 4 bit, that is 0, and then we add effective address 2000, that is the actual physical address will become 32,000 within hexadecimal. So, there are various modes in which we calculate physical address using effective address. So, we will see all these in detail in next slides. So, what is a addressing mode? Every instruction in microprocessor consists of two parts, that is opcode and operand. The way in which a microprocessor fetches opcode from memory is called as fetch cycle, and the way in which microprocessor fetches data from memory is called as execute cycle. So, there are different ways in which the operand is accessed in an instruction, which constitutes as addressing modes. So, in 8085, the overall addressing modes are divided into these categories, that is register addressing mode and immediate addressing mode is classified into one group, which are used to address operands from register or through immediate data. Next 6 instructions constitute addressing modes for memory data, wherein there is a calculation from effective address to physical address, and there are different ways in which effective address is calculated in 8086. So, these memory modes are classified as direct, register indirect, base index, base index addressing and string instructions. Next, the group of instructions are for IO modes or IO port, the way in which microprocessor fetches data from IO port. That are of two types, direct and indirect. When the address of IO port is directly specified in instruction, it is called as direct IO port addressing, otherwise it is called as indirect. Next is relative, where the relative address is specified in the instruction, and last is implied, where no operand is specified, only opcode will address what work needs to be done and on what data this work will be performed. So, in this way the overall instructions are classified into 12 types, that is register, immediate, direct, register indirect, base index addressing, base index string addressing, direct IO port addressing, indirect IO port addressing, relative and implied addressing. So, we will start from our first group, that is register mode. In register mode, the operands are specified in register only. In 8086, there are 4 16-bit registers AX, BX, CX, DX and 8 8-bit registers AH, AL, BH, BL, CH, CL and DH, DL. There are some registers to point out the address, stack pointer, base pointer, source index, destination index. One is flag register, and then there are 4 segment registers, that is code segment, data segment, stack segment and extra segment. And for code segment there is a pointer register called as instruction pointer. So, in 8086 the instructions wherein register holds the data is called as register mode instruction. For example, in case of move CL and DH, these both are 8-bit registers and this instruction copies 8-bit data from DH to CL. Some other examples like move AX, BX. So, here data is 16-bit and this instruction copies value of BX to AX. So, in any instruction wherein both the operands are in register only is called as register mode instruction. There are some of the do's and don'ts which needs to be used in describing register instructions. First, both the operands must be of same size, either byte or word. Second, destination can never be immediate data. Third, both the operands must be of register content and will not carry any memory data. Next is immediate mode. In immediate mode, 8-bit or 16-bit data is directly specified in the instruction. For example, move DL, 08. Here 08 is the 8-bit data which is directly specified in the instruction and this instruction copies 08 to DL register. Or we can say another example, move AX, 0A9F. So, 0A9F is the 16-bit data and this instruction just copies this value to AX register. So, immediate operand will always be source operand and it will never be destination operand. For example, we cannot write it as move 08, DL. This will be wrong. 08 will always be source, can never be destination. Next is memory addressing. So, as I have told you that overall memory addressed by 8086 is 1 megabyte and the address lines are 20 address lines. Whereas the largest or the register through which memory is accessed are segment registers and each segment register is of 16-bit. So we have to calculate physical address, that is 20-bit physical address, using 16-bit segment registers and offset, that is effective address. So we can say that the physical address calculation is segment register value, which is 16-bit, multiplied by 10 plus effective address, which generates physical address. And what are the values of this effective address? Effective address can carry index or pointer registers or some displacement. So effective address will be equal to base register, that is BP or BX, index register, that is SI or DI, or 8/16-bit displacement. So effective address can be calculated by combination of one or any two or all three of these values. So we can say that the physical address, the conversion from effective address to physical address will constitute various memory addressing modes. So this representation is also represented as segment register colon effective address. In this way we can express this example, that is effective address is also called as offset in case of memory addressing. So physical address will have to be calculated using segment registers and offset or effective address. So each time the processor want to access memory, it has to take the content of register, that is segment register, shift it to one hexadecimal place towards left. That is, if the segment register value is 2000, then to calculate physical address, it shift it to one decimal place and then add the required offset to form 20-bit address. Like if the offset value is 3000, then the required physical address will be 23,000 hexadecimal. We will take one more example as given here. If the segment register value is 89AB and offset value or effective address is F012, then the physical address will be 89AB, shifted one place to the left 0 plus F012, that is the required value will be 2C A 15 plus 9, 24 minus 16, that is 8 and 9. So this will be the required physical address, which is also called as absolute address of memory. So how different effective addresses are calculated, or how the effective address is calculated using either base or index or displacement or a combination of any two or three, will constitute different memory addressing modes. So we will start with the very first one, that is effective address, direct addressing mode. In case of direct addressing mode, effective address is directly specified in the instruction. It is just a 16-bit number which is specified in the instruction, and by default segment register will be, since it is optant, so it will be by default data segment. So for example, if the instruction is move bx, 1354, as this 1354 is in square bracket, so it is effective address. If there is no square bracket, then it is immediate data. So now the physical address will be calculated by ds into 10 plus 1354. Let data segment will be of have value 2000, then the effective address will be 2000 into 10, that is 20,000 plus 1354. So the effective address will be 21354 hexadecimal, absolute address. So the square bracket represents the content of the memory location, whereas if there is no square bracket, then it represents immediate data. So in similar way, we can also calculate the effective address of 0400 effective address. Considering same data segment, the physical address will be 20400. You can easily calculate this using same logic. Next is register indirect. In register indirect, the effective address is specified in one of the 4 registers, that is BX, BP, SI or DI, and the data segment is used for base or address calculation, that is data segment is used as segment register. So, the formula will be effective address let will be in BX like this instruction. So, physical address will be data segment into 10 plus effective address. Like in this example, let BX is 2000 and data segment is 3000. So, the memory address or physical address will be 3000 into 10 plus 2000, that is 32,000. So, this instruction will go to this address, copies the value of this address to CL. This value will be copied to CL. Then address plus 1, that is 32,001. This value will be copied to CH because this is a 16-bit register. So, effective address is given in BX register. Then base address will be segment into 10. The memory address will be base plus effective address. This instruction will take the content of that memory address to CL and address plus 1 to CH register. Now, base relative addressing is also called as based addressing or base relative addressing. Herein, only one register, that is BX or BP, is given in addition to 8-bit or 16-bit displacement. So, the BX plus 08 will give effective address. Let BX be 2000, DS will be 3000. So, the physical address will be 3000 into 10 plus 2000 plus 08. So, it becomes 32008. So, the one of the base register plus relative, that is displacement, will constitute the total effective address, and segment into 10 plus effective address will constitute memory address. We will go to this address, copies its value to AL, then address plus 1 value will be copied to AH in the very same way. Next is index addressing. In case of index addressing, as previously, base register plus displacement is taken in based addressing mode. Similarly, in case of index addressing mode, one of the index register plus displacement will constitute effective address. So, in this case, let SI be 4000 and data segment is 2000. So, the effective address will be 2000 into 10 plus 4000 plus 00A2. So, the physical address will be 2A042. So, this instruction will copy this address value to CX register and address plus 1 value to CH register in the same way. Moving towards base index addressing. In case of base index addressing, all 3 values, that is base register plus index register plus displacement, will be provided to calculate the physical address. That is, let BX be 2000, SI be 3000, DS be 4000. So, the effective physical address will be 4000 into 10 plus BX plus SI plus displacement. This will constitute A0, 0, 3 to 5 and 4. So, this will be the physical address, and this is construction copies address and address plus 1 values to DL and DH respectively. Now we move towards another set of instructions, that is string instructions. In 8086, string instructions are a class of instructions wherein microprocessor accesses a set of data and copies it from source location to destination location. So, in case of string instructions, the effective address is specified in SI, that is source index register, and destination or effective address of destination is specified in DI, that is destination index register. Segment register for SI is DS and for DI is extra segment. So, we can say that this instruction copies data segment into 10 plus SI, that is source value, to destination location, which is ES into 10 plus DI. So, if we talk about string instruction, the first value or the first address of source string is DS into 10 plus SI and first address of destination string is ES into 10 plus DI, and the next address will be considered plus increment or decrement will be based on direction flag. If direction flag is 1, then the next address will be calculated by decrementing the index registers, and if direction flag is 0, then next address will be called by incrementing the index register. So, we can say that for source location, effective address is SI, base address is DS into 10. So, memory address is base into base plus effective address. For destination, effective address is DI, base address is ES into 10, and the overall physical address is base plus effective address. And this instruction copies the value of source string to destination address. This is the starting location of source and destination. If direction flag is 1, next address will be SI minus 1 and DI minus 1. Otherwise, it will be SI plus 1 and DI plus 1. For example, if data segment is 2000, SI is 3000, ES is 4000, DI is 5000. So, physical address of source string will be 23,000 starting location, and physical address of destination starting is 45,000. If direction flag is 0, next address will be plus 1. So, next address हो जाएगा 23001 सोर्स का and 45001 destination का. Whereas, if direction flag is 1, then next address will be decremented, that is 23000 minus 1, which is 22FFF for source string and 44FFF for destination string. So, in this way we calculate, mind it, these are hexadecimal numbers, not decimal. So, the biggest value is F, not 9. Now, moving toward direct and indirect IO ports. In all the previous addressing modes, we have accessed memory, whereas in direct and indirect addressing modes, these are used to access data from IO port. There are two types of IO ports, or two types in which we access IO ports. One is memory mapped IO and other is IO mapped IO. In case of memory mapped IO, all the memory addressing modes are applicable for IO port. So, there is no need of any extra mode. Whereas, in case of IO mapped IO, we require two different type of addressing modes. In case of direct addressing mode, only 2 to the power 8 IOs can be accessed through instruction, and the 8-bit address is directly specified in the instruction. For example, in case of in AL09, 09 is the address of IO port. The value of this IO port address is copied to AL. Similarly, if it is out AL09, then the value of AL is copied to the address 09. Whereas there is one more mode, that is indirect. In case of indirect addressing mode, address is specified in DX register. In indirect addressing mode, 2 to the power 16 IOs can be accessed using 8086. The default register to access indirect port is DX register, which is 16-bit. So, DX will consist of 16-bit address which can be accessed using in or out instruction. For example, in case of out DX, AX, this instruction copies the value of AX to port address DX. Whereas, if we write in DX, AX, so this instruction copies the value of AX to the port address specified in DX. So, the content of AX is moved to port whose address is specified in DX and vice versa. Now, we take one more example of indirect addressing. We can also address this as move DX, 4000. So, 4000 will be the port address, and in AX, DX. So, this instruction copies the value of 4000 port address to AX. Now, relative addressing. In case of relative addressing, basically a instruction pointer is used and a 8-bit sign displacement. For example, JZ0A. So, jump if 0, then we will go to 0A. 0 is 8-bit. So, first of all we will convert it to 000A. So, if 0 flag is 1, then only it will calculate 0A, that is effective address will be IP instruction pointer plus 0A, and the base address for jump or for branching instruction, next opcode will be considered in CS IP, code segment into 10 plus IP. So, the effective address will be IP plus 0A, base address will be CS into 10 plus IP, and memory address will be CS into 10 plus IP plus 000A. So, if 0 flag is 1, then the program control jumps to this memory address. When 0 flag is 0, the next instruction of the program will be executed. Last is the implied mode. In implied mode, no operand are specified in the instruction. There is only opcode. Opcode will specify what to do and on which data it specifies the operation. For example, in case of CLC, this instruction states that it clears the carry flag. So, what it will do? It will clear, and which data? Carry flag. So, these are the different addressing modes used in 8086 microprocessor. Thank you. So, we have covered all the addressing modes of 8086 in this lecture. We will move to next topic, that is instruction set, in our next lectures. Thank you.